now we are talking of compressible flows, and we are talking of in particular isentropic compressible flows. And what we showed in the class last time was, if we have isentropic flow of a compressible gas, which is, and we assume inviscid flow. There's something else I'm missing out here. Then what we had was, what we showed was, we got to these relations. So, what I have written here, let me just start from the start. We had discussed some aspects of compressible flows and supersonic flows, and after that we came to the equations. If a gas is flowing, and we assumed adiabatic flow and inviscid flow of a compressible gas, and there we used the relations, we used the continuity equation, and we used the momentum balance equation, P1 minus P2 is equal to minus rho V1 square A1 plus rho V2 square A2, those type of relations. And when we got for a stream tube, we got these relations, and then we defined a condition called stagnation, which means if we bring the flow to a rest without any heat transfer in an isentropic way, if that flow is brought to a rest, we call that as stagnation. And what we showed then was T0 upon T, if we define a stagnation temperature, which means if the flow from whatever state it is brought to rest. Now, a stagnation state may not exist in a flow. If the fluid is flowing, it just keeps on flowing, there is no stagnation state. So stagnation could be a hypothetical state, or it could be a real state. For example, if there is gas in a chamber and we want to pull this out. So therefore, we will reduce the pressure outside the chamber, and that is what will cause the gas to flow. So that means it starts from stagnation conditions and it comes out through some sort of a pipe from where it is flowing down. Okay, so in this course we will restrict ourselves to equations of inviscid flow. That is why we will go only up to section 9.6. We will not talk of flows with friction or flows with heat transfer. Those can be extended just by those extra terms which we have neglected. So if you come across that situation, you can read those sections of the book or similar sections in other books and analyze those equations. So for isentropic flow, for adiabatic flow, we find the relation between temperature is related to the local Mach number. If the stagnation temperature is T0, then what we find is the temperature can be given by this equation. T0 by T is equal to 1 plus K minus 1 by 2 Mach square. Well, of course, here again, it is not a direct equation in that sense because Mach also contains temperature. Because in Mach number, you have square root of, it's the local Mach number at that point, which means it's V by C, and C is not constant. So now you have to get used to when we are talking of a flow situation, the speed of sound is also changing from point to point. Because it's directly, for ideal gas, it is square root of KRT. So what I wrote a compressible gas, ideal fluid, that is what I was thinking, ideal gas. So we have freely used the ideal gas equations. Similarly, we can define what would have been the speed of sound in the stagnation state to the local speed of sound. That also, and everywhere we find 1 plus K minus 1 by 2 Mach square. It is something to power of this. So I start calling this as a variable alpha. 1 plus K minus 1 by 2 Mach square, I will call alpha so that I don't have to write it again and again. Now, the flow could be adiabatic, but if it is also isentropic, then in an isentropic flow, for ideal gas, we have relations which relate state of two pressures and temperatures with the help of gammas, what we have seen, or Ks. So this relation P0 by P is equal to T0 by T, K to the power of K minus 1. This is what you have seen in thermodynamics as isentropic flow relations. So those also we can use, and using this we can find a relation between P0 and P. So this is not rho, this is P, and we can find a relation between rho 0 and rho. Now, once again, let me clarify before somebody asks me, you will not be asked to remember any of these formulas. These formulas either will be given, and in fact what I'm going to give is not the formula, I will give you a table where these values are, and let me explain how these tables work. And even in today's age, the tables look archaic. Why? Because all this data will be fed in some table which your computer can directly use. So if you have to use these problems in real life, you don't even need to use the tables. But the reason why I will give those tables to you is so that you understand what the computer does when it does these calculations. Because there has to be a difference between an engineer and a mechanic. A mechanic knows how to use the tools, but doesn't understand what goes on inside. But as engineers, I would expect you to understand what this black box which is turning out this data actually does. Because often we may get very wrong results by using a black box because we don't understand what it is doing, and we may miss out some subtle thing. So that's why that will be important. So here what we look at is, what we find is, if we look at all these quantities, temperature, speed of sound, pressure and rho, all these are function of Mach number and the stagnation state. So what one can see is, if I plot a graph where on the x-axis I will have the Mach number, and when Mach number is 0, what state does it represent? It represents when V is 0, so it will correspond to the stagnation state. Okay, so isentropic relations are often presented in a graph like this. So for example, here, if I want to plot T by T0, what will be the value of T by T0 on the y-axis? What's the value of temperature when Mach number is 0? it will be T0, so therefore, as you rightly say, this will be 1. Okay, and what you find is if you plot this curve, this is a T by T0 curve, which means as Mach number increases, the temperature decreases. Now, similarly, when we plot, this is another curve for rho by rho 0. Once again, so all these say as the speed increases, the corresponding variable is decreasing. And the third curve we have is a more drastic curve. This is for P by P0. So this is isentropic flow of ideal gas. I think what's happening is so we have these different states. At Mach number 1, you will, for example, get the value of T by T0. So now, of course, for these curves, that means if you will talk of these curves for air, then you will put K is equal to 1.4. Okay. Now, what we do is just as we have the stagnation state, which we denote by 0, there is another state we denote the sonic state. What do you mean by sonic state? Mach number 1. And we use a subscript star for this. So which means rho star, P star, T star, A star, these are the values of rho, P, T and A at Mach number 1. And what we find is for air, P star upon P0 is equal to 0.5283. These are just some numbers to give you an idea. And what this tells you is that suppose you had a stagnation pressure. And from that absolute pressure, you bring it to a state where the pressure is only 53% of what it started with. So suppose the gas is in a container where the pressure is 10 kilopascal. Or whatever the right number would be, kilopascal, it should be more, 10 to the power of 4. So, no, it should be more because 1 kilopascal would be 100 kilopascal would be the atmospheric pressure. So let us say there it is something like 500 kilopascal. So if from there isentropically from 500 kilopascal absolute pressure the gas flows to a value where the pressure drops to 250 kilopascal, then P upon P0 will become 0.5. So which is less than 0.52. That means the Mach number already would have gone more than 1. So even with half the drop of pressure for air, you find the speeds become equal to speed of sound and the flow becomes totally compressible. So therefore these pressure changes in liquids, of course, this will be very drastic. You don't need at half the pressure drop it will probably be a fraction of the Mach number. But for gases, even a reasonable drop of pressure can lead to flows which are compressible. Okay, so therefore that's why then one tends to use these things. Okay, so now next thing, what do we do? So in fact I can add one more number here, A star upon A0. So now one thing you realize is that if you have to use these relations, there are two ways in which you can right now use them. Way number one, I have the formula given to you. So if I know the Mach number, I can find the corresponding, I calculate the value of alpha, I calculate the ratio. That is how these graphs were done. Second way is, if this graph is given to me, then I can just read it from the graph. Third way is, if a table of this graph is given to me, then I can look at the nearest value and get to the table. If it is somewhere in between, I can use interpolation. So these are the three ways. The tables I'll give it to you in the next class. So this is how one can look into this. There was one more thing which I thought I will discuss with you. That was the... Now, the other thing was this star thing which I talked of. Once again, the sonic conditions may again, for a given flow, may be hypothetical. It is possible that the flow never reaches the sonic condition. Suppose if it is in a nozzle, it starts from a very low Mach number, goes up to Mach number 0.8 at the exit. So it is an isentropic flow, you can get those values from the graphs, but it has not reached the sonic state at all. But still I can define a star state for that flow. So the sonic state could also be taken as an ideal state, and that role of that will come in when I discuss further things. So it may reach, just as the stagnation state is there, it may never reach that value, or it may reach that value. Now, what we want to do next is, we'll look at one-dimensional flow in a variable area duct. So I can make a duct to be of a general shape. It could have a shape like this, or it could be one part of this, the left part, the right part, it could be expansion, it could be contraction, or a mixture. So I'm just showing all this to you, that this is, in general, this is what we are talking of. Now when I talk of 1D flow, first of all, if it is two-dimensional, in general, we will have, for 2D flow, it would be Vxi plus Vyj, and Vx and Vy would be functions of xy. Okay, this is what you would expect, but if area change is gradual, that is dA by dx, this is the x direction, is small. So then we will have this we have done in our integral flow analysis. In almost all the problems we have assumed one-dimensional flow, velocity is just a function of x. So now in such a flow, x is this direction. So now at any station x, at this station x, let the density be rho, let the velocity be v, let the pressure be p, let the temperature be t. And so they don't change across the cross section. These are all functions of x. These are the properties we are talking of. So now, what type of equations we can write? So if we apply mass balance, tells us rho of x, v of x, a of x, as long as the flow is confined to this tube, this must be constant. Okay, so now we do a logarithmic differentiation. So we get fine. Now we assume this to be inviscid flow. The momentum equation for the inviscid flow will give us if I take two sections which are almost a thin strip. So in fact, rather than this water, and I differentiate. So this is a very thin strip. This is 1. This is 2. Area is the same. So I'll get P1 minus P2 into area will be equal to minus rho V1 square A plus rho V2 square A. And there when I apply this, I get P1 plus rho 1 square is equal to. And if I differentiate this, what I will get is dP upon rho plus dV VdV is equal to 0, because this is going to lead to P plus rho V square is equal to constant, and when I differentiate this I get dP plus rho 2 rho V dV. There's a 2 also, 2 kahan gaya? dP by rho. Am I missing out something? No. 2 V square का एक मिनट रुको, क्या क्या है? टू होगा नहीं तो इसमें it should not be 2. Let me just see. I think I'm missing out something. Now this basically, then this is not coming from here. Let me just remove this. This comes from, then I use the, let's just see. This is dP by rho plus V dV is equal to dP. I have got a relation here. dP by rho. I think let me move with this. I'll just continue ahead and then I'll get back to you on this. Let me just. So this is the equation which we get for. I think there the mistake I'm making is I'm assuming rho to be constant. So if I take the variation of rho, then it will take a form like this. I'll get back to you on in the next class, because let me move ahead with this. And then what we have is dP by d rho. This is equal to a square. So I can write dP is equal to a square d rho. And when I do this, I get a square d rho by rho plus V dV is equal to 0. And this gives me minus rho V dV is equal to a square d rho. And this we put in mass balance. So So when I put this in mass balance, I have d rho by rho. So I will get minus rho v dv upon a square rho plus dv by v plus dA by A is equal to 0, and this gives me dV by V common into 1 minus from here what one can get is dA by A So for a flow in a duct, I get a relation like this. dA by A into 1 by max square minus 1 is equal to dV by V is equal to minus dP upon rho V square. And you see this particular relation, well, you can go in the nitty-gritties of the derivation, but this is the main thing. And what we'll realize here is that how the sign of dV by V will change depending on the value of Mach number. If Mach number is bigger than 1 or less than 1, the sign of dV by V will change because there is a function Mach square minus 1. So if Mach square minus 1 is either great, if Mach is greater than 1 or less than 1, these signs will change. And that is what makes this thing very... So let's look at a case. Let's start with the case of a converging channel. In a converging channel, and let us look at the case when Mach number is less than 1. Now for a converging channel, all these variables are with respect to x. So dA is less than 0. That means as we are moving ahead, converging channel means we are talking of a case like this. Area is reducing as we increase x. Now if Mach number is less than 1, then what happens to this? Mach square minus 1. This is negative. So that means dV by V is negative. dA is less than. So in this case then what we have is dV is positive and dP is negative. So now if that is the case, that means what happens to the velocity as x increases? dV is positive, so it increases and pressure reduces. So that means this is what we call as a nozzle. And similarly, if we look at the Mach number greater than 1, less than 1 case for a diverging channel. Diverging channel means it is something like this. So here dA is bigger than 0. So therefore dV is less than 0 and dP is greater than 0, which means this is a diffuser. And let me put this slightly below. When Mach number is bigger than 1, then we find the opposite trend. That if in a converging channel where dA is less than 0, dV will be less than 0 and dP will be greater than 0. That means as the flow moves in a converging channel, which is something very unphysical from a compressible flow viewpoint, that as the flow moves like this, and if Mach number in this case is bigger than 1, then the velocity will reduce as x increases. This is what I mean by writing dV is less than 0. And pressure will increase as x increases. So this is something which we did not expect. We have now, having done this course and for so long done all these problems, V1A1 is equal to V2A2. We are so used to thinking that velocity will always increase in a converging channel. But we find the opposite effect here. And why this is happening? Because the density has reduced much more. So it's basically rho V1A1 is equal to rho V2A2, rho VA. So the density also plays a role, and the change of density becomes so much more important that it overtakes the effect of velocity. Okay? So that is what happens when Mach number is bigger than 1. And so a converging channel which happens to be a nozzle for a subsonic case becomes a diffuser. And similarly, in this case, dV is greater than 0, dP is less than 0. So this becomes a nozzle. And if I look at the value of dA upon A, this becomes equal to Mach square minus 1 dV upon V. Now, of course, what the question which comes is that these things happen to be so this thing. But what happens if the flow encounters both the things? A subsonic as well as a supersonic this thing in a channel. Can that happen? Now, what you realize is when Mach number equals to 1, then dA upon A has to approach 0 if the flow has to be isentropic. So, this we observe in a very interesting effect, that when we see flow in a converging channel, let us now apply this. So I have a flow like this. It starts from a value P1. This is the exit, and the pressure here is, let us say, PB. So now we are looking at flow in a converging channel. If PB is equal to P1, if the back pressure is the same as where it starts, then you realize there will be no flow. You want to start the flow, so maybe if it's a stagnation condition, there will be no flow. Then what you do is you start to reduce PB. You reduce PB, the flow starts. That means PB upon P1 is less than 1, will start the flow. Now we reduce PB the flow speed will increase. And the maximum velocity is at the exit. Now, you will reduce this further, so a value of PB comes where PB upon P0 is equal to P star upon P0, that is, PB has been reduced to the value of P star. What is P star? Such that the Mach number becomes 1. The velocity keeps on increasing, you keep on reducing the pressure till you reach Mach number 1. Now the question comes, what happens if you reduce the pressure further? If you reduce PB further, what will happen? Now, the change in area, it is a monotonic channel, the area is the same. dA is always negative. You can't, dA is not becoming 0. Area is reducing, so dA is negative. Now what will happen is if you reduce PB further, then the flow in the channel stays the same. It will stay that just till the end of the channel, it becomes sonic. And then the reduction of pressure further from P star to PB will happen outside the channel, because in the channel there is no mechanism how the pressure can be reduced further. The Mach number cannot become bigger than 1. In a converging channel, if we start with a subsonic flow, the maximum Mach number we can attain is 1. So if the back pressure is such that the Mach number there has to become bigger than 1, it will not happen. The flow in the channel will stay same. So if you reduce PB further, then what happens is the flow in the channel, or I shouldn't use the word channel, in the converging section stays same. That is, for PB less than P star, at the exit Mach number is equal to 1, and the reduction of pressure from P star to PB occurs outside the nozzle So this again is something which is very contradictory, because you expect that as you keep on reducing pressure, flow speeds could keep on increasing, it should just go on increasing, but that doesn't happen. And this flow is said to be choked. This is the term which we use, and choking occurs only in compressible flows, that if the isentropic conditions demand that the flow should have a Mach number bigger than 1, it will not be possible. So the maximum flow rate which you can get in a channel in this nozzle will be what corresponds to Mach number 1 at the exit. If the pressures are such that it is lower, then still the flow rate which you will get will be corresponding to Mach number 1. And that is what is often used to calibrate devices. Because we know once if I choke the flow in there, then the flow rate is known to me. It will be corresponding to Mach number 1, corresponding to whatever stagnation conditions it started with. And we'll look at some problems to see how we solve this. I'll look at some problems in the next class, and maybe also in the tutorial. I'll make a tutorial, I'll make a homework sheet for you where you'll have to solve these problems. And most of these, the best way to do this will be to use the table. I will also hand out a table to you. You'll be allowed to bring the table to the exam. So look at the nearest values which are given and work out the values from the table. So we'll have a look. In the next class, we will see some of this. Now in the next class, we'll also look at one more phenomena. So from here, what we realize is, if I want to get Mach number 1 in a tube, I want to get a flow with Mach number bigger than 1. How do I attain that? And suppose I'm starting from stagnation condition, then obviously to get Mach number 1, I will have to get a converging channel. If I put a diverging channel, it will not work. If it is a subsonic flow to start with, I exceed, but then what I realize is this at this exit or at this point where the area is the lowest, maximum Mach number which I can get is 1. Now if I want the Mach number to be higher than this what should I do? I have to add a diffuser or a diverging section. We should use diffuser because it will be a nozzle again. So we have to add a diverging section to this tube from where once the Mach number has reached 1, then it can become bigger than 1. And that is the only possible way in which I can do this. That I have to add a diverging section to this. So in the next class we will look at what is called converging diverging duct. We have seen flow in a converging duct here. And based on back pressures, we'll see some problems. We'll be able to decide depending on the value of back pressure and the stagnation condition whether the flow is choked or not. Because for choking, what has to happen? The ratio has to be 0.5 to 83. If it is less than that, the flow will be choked. So there are two things we'll look in the next class, the converging diverging duct. But before that, another phenomena happens. So choking is one thing which happens. The second thing which we come across is the phenomena of shocks. So first we will study shocks because they happen in a converging diverging duct. And then we will study flow in a